Alright, in this video we are going to go over the step response of what is commonly called an RC circuit. RC circuit because it has a single resistor with resistance R and a single capacitor with capacitance C. It is called the step response because we are sending a step input to that circuit. So we have our input voltage here to the resistor, and we measure our output voltage over here in between the resistor and the capacitor. And a little sneak peek, or the graph you might be familiar with if you are looking for an explanation in this video, if we plot the voltage across the capacitor over time, it's going to look something like this. And there is a parameter called the time constant tau that tells us something about how quickly this graph rises. So in this video, we are going to learn all about the underlying equations that you need to analyze this circuit and the behavior of this graph. Before we do that, I want you to just forget about electricity for a second, because this video series is Intro to Electronics for people who are not electrical engineers, and it is usually a lot more intuitive to talk about other physical systems that don't involve voltage. So, for example, imagine that the y-axis of this graph is temperature instead of voltage. And I just have a glass of cold water that I just took out of the refrigerator and plopped on my kitchen counter with air at ambient temperature TA. So it's probably pretty obvious or intuitive, hopefully, that say initially that glass of water is going to start out at some initial temperature, we'll call it T0, and we're not dealing with any phase changes or anything. This isn't your physics class, there's no ice initially. The temperature of that water is just going to rise a little more quickly at first, as it's driven by that larger temperature difference and heat exchange with the environment, and then kind of slow down and asymptotically approach the ambient temperature TA. It's not going to overshoot. It's not going to somehow get warmer than the ambient temperature or get warmer and then cool back down. It's just going to approach the ambient temperature. And the same thing would happen if I put, say, a cup of hot coffee on the counter that was initially at some higher temperature. It's going to asymptotically approach and then eventually reach what we call steady state, where it is no longer changing at some point in the future. And you could pick some other physical variable here, say velocity for terminal velocity of a falling object, and the underlying math might not be exactly the same in all of these cases, but the kind of basic principle that this is what we mean by a step response. There is just one instantaneous change at the beginning, whether it is the application of a force or a change in temperature, or in the electrical case, the sudden change in an input voltage, but that's it. You only have one change in your input, and then nothing changes forever until you eventually reach a steady state, as opposed to something like driving the input with a sinusoid, which is going to be a different topic in a future video. So again, it can be a little more confusing conceptually to visualize what's happening with voltage in a circuit like this. So think about a different physical system if that kind of helps you more intuitively understand what's going on. So our goal for this video is going to be, ultimately, we want to be able to plot this graph. We want to be able to plot, whoops, I accidentally leave presentation mode, plot V out of t versus time for a circuit like this with a given resistor R, capacitor C, for an input where we have some amplitude of voltage change here. And quick note, this video is part of a playlist, so the previous video introduced capacitors. We have a ton of videos about resistors before that, so check out that playlist linked in the video description if you need that background information, because we are kind of assuming some prerequisite knowledge here about the components in the circuit. Now, before we continue, we are going to need a little more background information that we are going to need to in order to analyze this circuit and get the equation that's going to give us the behavior of this graph. So I am going to write down a differential equation, but this is not a differential equations class, so you are just going to basically take my word for it that we have the solution to that differential equation in this very specific case. So if you've taken differential equations before, excuse me, sometimes that will be a prerequisite for an electronics class. This may look familiar to you. If not, don't worry about it too much, because ultimately we're going to get an algebraic equation that will give us the shape of this graph. So the differential equation I'm going to write down is a first order differential equation where we have a parameter tau times dx dt, that is the derivative of some variable or parameter x. I don't care what it is. It can be voltage, it can be temperature, it can be velocity. And as I mentioned in the last video, depending on where you took your calc classes, you might see this written as x dot or x prime or whatever. It doesn't matter how you write your derivative. So I have tau times t dx dt plus x of t equals ks, which is a constant, times some forcing function f of t. Now, this is a differential equation just of this form. First order differential equation, first order meaning I only go up to the first derivative. For the specific case of the step response that I mentioned earlier, where this forcing function is just, everything is 0, and then this just goes up to a constant, I know that the time domain solution to this differential equation is x of t equals x of 0, which is the initial condition, minus x of infinity, which is the final or steady state condition that we talked about in that graph earlier, times e to the negative t over tau. Please pardon my lousy handwriting, and hopefully you can tell the difference between my t's and my taus, plus x of infinity. Again, that's the final or steady state condition again. And again, where that parameter t, tau, is the time constant, which is the same thing that we have in the original differential equation over here. Now, again, how do we get from here to here? As far as this video is concerned, magic. We are just taking this for granted. If you want to see where this comes from, you need to go take a differential equations class. That's not what we're doing in this video. We are just concerned about this specific form of the equation and this result for the step response. Now, the other thing, or relevant background information we're going to need here, is a reminder about Kirchhoff's voltage law and Kirchhoff's current law, abbreviated KVL and KCL. So you may remember these as voltages add in series and currents are the same in series, is kind of the colloquial way of saying these. So we have a ton of previous videos where we see these for resistor and battery circuits. So for example here, I would say, okay, these resistors are in series. So if I call this R1 and R2, then I know the current I1 has to equal the current I2. And say if I call this voltage of the battery, then I know the voltage of the battery has to equal the voltage over resistor 1 plus the voltage over resistor 2. So again, that is all review covered in the previous videos in this playlist. That's why I went through this really fast there. The important part as far as this video is concerned is that these two laws apply regardless of what these things are. Okay, so it doesn't matter if these resistors, these also apply to capacitors and inductors, which we will talk about later. So more generally, if I just have something VA, and if I follow my sign convention, which we talk about in some earlier videos, say I have thing VA with voltage VA across it, thing VB, thing C, this just sounds like a Dr. Seuss novel or something, then the Kirchhoff's voltage law here is still VA equals VB plus VC. Doesn't matter if these are resistors, capacitors, inductors, or batteries, okay? This law still applies, and then same thing here. This, I've redone my subscripts a little bit, but IB equals IC, which is going to equal IA plus or minus a minus sign, depending on how you're doing your sign convention. But these two things apply to resistors and capacitors, which is going to make them useful for analyzing this circuit. So that's what we are going to do on the next slide, because things are getting a little crowded in the corner here. But a brief reminder at this point, if you kind of just got lost in, okay, why are we doing all these equations? Why are we talking about this? From a practical aspect for why you, as, say, a mechanical engineer, would care about this, basically the idea is that voltages don't change instantaneously. Just like in physical systems, temperatures do not change instantaneously. Things do not usually immediately teleport from one place to another. Okay? voltages, even though we usually can't see it, because on a human time scale, they usually change very, very fast, and it might seem almost instantaneous when you flick your lights on or something. Voltages also take time to change, and if you're doing this in a lab course and you zoom in with an oscilloscope way faster than the human eye can see, voltage doesn't just change immediately, and this can have effects in electrical systems. For example, if you're working with an Arduino in a microcontroller class or a mechatronics class or something, those digital pins that you flip on and off don't actually change on and off immediately, right? There's a time constant to them, because even in a circuit without a physical capacitor that you've put in a breadboard, there is something called stray capacitance, so basically just extra capacitance in a circuit between parallel wires or parallel rows in a breadboard or something. So the real world, just like how the real world has friction, even though you model things without friction in lots of physics problems, real circuits are going to have capacitance and things aren't going to change instantaneously. So a little reminder of why you care about this before we dive more into the analysis on a clean slide. Okay, so let's redraw the circuit, start over with things a little neater here. I'm going to draw it a little differently this time. We're going to have some voltage source, Vs, connected to an ideal switch, so we're not worried about bouncing or anything on the switch. Connected to my resistor R, my capacitor C, which is connected to ground, and we are going to measure V out here in between the resistor and the capacitor, so that is equal to Vc, my voltage, over the capacitor. Now, you might also see this sometimes driven with a square wave. We're only worried about, basically this is like saying we're driving this with the first period of a square wave where we close this switch at time t equals 0, and our goal is to find, oops, something at the top of my drawing tablet doesn't like when I swipe down from the top of the screen there. We want to find a graph for Vc or Vout as a function of time. What does that look like? So our goal is to analyze this circuit and come up with that equation. And this is where, as a mechanical engineer, you may feel like a fish out of water and say, well, how am I even supposed to start analyzing that circuit? Like, I know Ohm's law, I can do stuff with just resistors, but how do I do things with a capacitor in them? And my tip there is to start, again, it really doesn't like when I write too close to the top of the screen, use KVL and KCL. Apply them to the circuit and write down the equations that you get. So in this case, if I apply Kirchhoff's voltage law, I see that after that switch has closed, the voltage of the source is going to be equal to the voltage across the resistor plus the voltage across the capacitor. That's just adding those two voltages in series, setting them equal to the resistance of the source. And if I apply KCL, I know that since the resistor and the capacitor are in series, the current through the resistor is going to have to equal the current through the capacitor. Now, if I remember what we did on the previous slide, I had that differential equation I'm going to write with a different form now. Instead of x, I'm going to write it in the output variable that I want, tau times dvc dt plus vc of t equals f of t, where k f of t, where f is some, in this case, step function, and k is a constant. Ideally, I want to get these equations into this form somehow, because if I have a differential equation of this form, then I know, again, the time domain solution of this equation. I'm going to have Vc of t equals, pardon as I have to flip back to the previous page of my paper notes here because I got jumbled up and didn't have that equation memorized. There we go. Make sure I get this right. Vc of t is going to equal the initial condition for V minus the final condition. I wrote this a little too close to the edge, times e to the negative tau over, negative t over tau, plus, I got way too close to the edge there, the final condition again. So I want to get here, that will allow me to get here, but I am starting with these two equations. So how do I sort of massage or move those around into this form? I have two other equations that we haven't written down yet. There is trusty Ohm's law, which I know will always apply to a resistor. So in this case, that's going to be the voltage across the resistor equals the current through the resistor times R. And I have the equation for a capacitor, I equals C dV dt. So in this case, I'm going to slap subscripts on there. The capacitor current equals C times the change in voltage dt over the capacitor. But since I have my KCL here, I know that those two currents are equal. So this is going to allow me to start working with my equation and do some algebra to get to this form. So I'm going to rewrite Vs equals Vr plus Vc. Vs is a constant. Ideally, I want to get rid of the Vr and get this whole equation just in terms of Vc, which is the variable I'm interested in. So I can sub in Ohm's law for Vr there. That's going to give me Vs equals IR times R plus Vc. But I know that thanks to Kirchhoff's current law, IR is equal to IC. So that's IC times R plus Vc. And now I know, thanks to my capacitor equation, again, I want to get this whole thing in terms of Vc and its derivatives, so I can have a first order differential equation just in terms of Vc. I know that my capacitor current is equal to C times dVc dt, so I can plug that in here, and I get Vs equals C times dVc dt times R plus Vc. And I now have something that looks suspiciously like that. I just need to rearrange things a bit. So if we just, switch my pen color back to white, rearrange this equation a little bit to look like that one, we are going to move the R over in front of the derivative here and put that term on the left side. So we have RC times dVc dt plus Vc equals Vs, which is a constant. And again, now this equation is in the form of the one we were talking about at the beginning, where we have a constant, we'll talk about that more in a second, times the derivative of the variable we care about, plus the variable we care about, which is equal to some constant forcing function. And the crazy thing here, kind of, again, it might seem weird that we kind of just, I told you to take this equation for granted, and that's what we were working towards, is that, again, this time constant, tau, describes how long it takes the response to get towards steady state. So I didn't mention this in the beginning of the video, but again, this axis is time, this axis is voltage. A single time constant, so 1 tau, is how long it takes the response to get 63.2% of the way to steady state. I didn't draw that perfectly there. So when you hear a professor or somebody mention a system with a longer time constant or a slower time constant, that just means it takes longer to get there. So something with a longer time constant is going to take a longer amount of time to get 63.2% of the way to its final value. And the crazy thing about an RC circuit is that that time constant tau is equal to R times C. And I am not going to do the SI unit gymnastics to prove this, but that means you have something with units of seconds equal to ohms times farads. So these are electrical units. Again, when you're learning Ohm's law, you learn amps, volts, ohms, all that stuff. Capacitance is farads. Turns out that if you multiply an ohm times a farad, you get a second, which is probably not an intuitive result at all. Again, I'm not going to prove it in this video, but you can go look it up on Wikipedia and see all the unit conversion that will get you from here to here. So just knowing the resistor and capacitor value of a circuit gives you the time constant. And if you are designing one of these circuits and need to select or choose a specific time constant, you can figure out what, based on the resistors and capacitors you have available, multiplying their values, what time constant it will give you. Okay, so we have the time constant. Remember that our ultimate goal is to get an equation for this graph. We have the time constant, but we still need the initial and final conditions to fill out this equation. So to find those, we're going to have to remember some rules for a capacitor, which we covered in the previous video. One is that for continuity, voltage must be continuous. Again, this is talked about in more detail in the previous video in this playlist. Voltage must be continuous. And in steady state, a capacitor acts like an open circuit. And those conditions, pardon my terrible handwriting, are going to help us find out what the initial condition is here and what the steady state condition is here. I'm going to try and cram this all in at the bottom of this one slide. So I'm going to redraw a graph here with voltage over the capacitor on the y-axis, time on the x-axis. And when this switch is open initially here, as long as there's no initial charge on the capacitor, there's just nothing going on. So the initial charge on that capacitor is 0. The voltage on it is 0. So just for all time back to negative infinity, we just have no voltage across the capacitor. Then at time t equals 0, the switch closes. So we don't know yet what is going to happen after that. But we know immediately at time t equals 0, thanks to our continuity rule here, we know voltage must be continuous over the capacitor. So I'm not going to have a jump in voltage over the capacitor. So the voltage at t equals 0 also has to be 0. So that is my initial condition, Vc of 0 equals 0. And then we know that in steady state, so pretend I haven't shown you this graph yet, and I ask you, after the switch has been closed for a long time, what is the voltage over the capacitor? So I have a circuit with, excuse me, a battery with voltage Vs, a resistor R, and we're just pretending that the switch is closed. It's like the switch is not there. It's just a closed circuit. And the capacitor C. What is the voltage Vc over this capacitor in steady state after the switch has been closed for a long time? Well, looking at switching pen colors again, our steady state rule, we know that in steady state, after the circuit has reached a constant state, a capacitor acts like an open circuit. Well, if there is an open circuit, then I know the current must be 0, right? So there's no current through this capacitor in steady state. So what is the voltage at this point in steady state if the current is 0? And this is something that actually trips a lot of students up. I asked this question in a previous video with an open switch instead of a capacitor, but again, if it's an open circuit, same concept. A lot of students will look at that and say, well, oh, there's no current, and you think of Ohm's law, V equals IR. Well, if there's no current, then there's no voltage, so the voltage must be 0. And that is sort of a misapplication or misunderstanding of Ohm's law. Remember two things here. One, Ohm's law applies to resistors, not capacitors. And two, voltage is a difference between 2 points. So you talk about voltage drop between 2 points. So you can apply Ohm's law here, but Ohm's law applies to the resistor. So V equals IR. If the current through that resistor is 0, the voltage drop across this resistor is 0. So if the voltage here is Vs, and sorry this is getting a little crowded, and the voltage drop across the resistor is 0, then the voltage there is also Vs. So the voltage across the capacitor is not 0. The voltage between the top of the capacitor and ground is not 0 volts. It is equal to the battery voltage. So again, sometimes people tend to just blindly or apply Ohm's law in a bit too much of a hurry there and just assume, oh, if current is 0, then voltage is 0 everywhere. Not the case. The voltage drop across the resistor is 0, so the voltage across the capacitor is equal to Vs, which now makes sense if we talk about the graph we were seeing earlier and just kind of thinking about this intuitively, that when you close this switch, initially your capacitor is at 0 voltage, but, I'll switch my plain color again, it is gradually going to charge up to Vs, the battery voltage, in steady state, but it's never going to exceed that. It's impossible for the capacitor to somehow get more voltage than the battery is providing. So that gives me my final condition, Vc of infinity, and I know my high school calculus teacher would yell at me for not writing this as a limit, VC limit as t approaches infinity, but I'm an engineer, so I'm allowed to be lazy about it now. VC of infinity equals Vs. So now we have all three of the constants in this equation. We have Vc of 0, we have Vc of infinity, and we have tau. So we can finally write our equation for that graph. Vc of t equals Vc of 0, which is just 0, minus Vc of infinity, which is Vs, times e to the negative t over tau, which is Rc, plus Vc of infinity, which is again Vs. So you can, that's technically correct, but kind of an ugly form of the equation. You can do some algebra to rearrange that and write it as Vc of t equals negative Vs e to the negative t over Rc plus Vs, and then again you can rewrite that for the final form of the equation, Vs times 1 minus e to the negative t over tau, where again tau is equal to Rc. So there you have it. All of that work to arrive at this final equation describing the time response or the step response of an RC circuit to a step input where you are either closing a switch or driving this with a square wave. We were only talking about kind of the first rising edge of that square wave there, so from something like a function generator. But if you then have the falling edge and continue this, and this is what you'll see if you do this in a lab and hook this up on an oscilloscope, and I don't want to start a new slide here, so I'm just going to cram this in over in this corner. If you are driving this with a square wave from a function generator, and then looking at the output on an oscilloscope, what you'll see is the rising step response and then falling step response. Okay, so this is a very common intro lab activity that you will see on an oscilloscope, and as long as the frequency of your square wave is low enough, then your RC circuit will get to steady state. If your square wave is too fast, then rather than seeing something like this, where it's getting to steady state each time, you might see something choppier where your square wave is too fast and it is not getting time to reach steady state. So again, that is a very common introductory electronics lab, and if you are asked to do something like compare your experimental results, so the graph you are seeing on the oscilloscope, to the theoretical result, and what that graph should look like, this is how you do it. You need to know the voltage or amplitude of that source, and you need to know the resistor and capacitor values so you can calculate the time constant and plot this equation. So in the next video in this series, again here we were talking about what happens when you drive this with a constant. We are going to look at what happens when you send a sine wave in here and introduce the concept of a filter that can filter out low and high frequency signals.